Hello. Okay. Good afternoon. My name is Gore Yu. I come from National Zhongzhen University, Taiwan. And today my topic is related to novel slang based on quantum behaved particle swarm optimization. Here is my outline. First, I will give some introduction about the idea. And the next, I will introduce the hardware configuration. And next will be the G-mapping algorithms. Next will be the quantum behaved particle swarm optimization algorithm. And next will be the novel slang based on quantum behaved particle swarm optimization. And the next will be the simulation and the experimental result. Final will be the conclusions. The applications code router has been widely developed these years. So SLAM constructs the digital map and localize the position of the flying robot. SLAM is used for AGV moving in smart factory or pace planning in indoor office. And this paper combines code router with SLAM for outdoor environment. Here is the specification of the code router. The processor will be 32-bit ARM Cortex, and the controller will be the Pixhawk version 2.4, and the firmware will be the Arduino Copter version 4, and the sensor will be the gyroscope and the LiDAR. So here is the spec for the hardware. The processor will be the ARM Cortex, and the interface will be the micro HDMI ports supporting dual displays. And here is the RP LiDAR sensors. The measurement range will be 14 meters, and the frequency will be 9,200 Hertz. Here is the structure of the helicopter with the RP LiDARs. And this figure shows the system communication path. And the next, I will introduce the G-mapping algorithms. G-mapping will use the real black realized particle filter. And we have, in this algorithm, we have two models. The first one will be the observation model. Second one will be the motion model. In the motion model, we can use a particle filter to estimate motion model. Each particle represents a potential trajectory of the robot. And in the observation model, the maps are built from the observations, and the trajectory represented by the corresponding particle. The posterior over measurement model can be computed using mapping with non-poles. So in general, the weightings of proposed distribution is not same as the target distribution. If the proposal distribution is same as the target, the weighting of particles are all equal. And we can obtain a recursive formulation to compute the importance weighting by restricting the proposed to fulfill the following assumption, the equation 4. So based on equation 4 and 3, we can obtain the weightings as equation 5. In equation 5, the eta is a normalization factor resulting from Bayes' rule. So to solve the problem integrating ZT into the proposed distribution can make the model focus on overlap regions of the observation likelihood. So based on equation 5 and 6, we can obtain the computation of the weightings. So to efficiently draw the next generation of samples, we can compute a Gaussian approximation based on the data. So the Gaussian parameters are estimated as equation 8 and 9. And the equation 10 shows the normalization factor eta. So in this way, we can obtain a closed form approximation of the optimal proposal. Using this proposal distribution, the weightings from equation 7 can be modified as equation 11. And next, we will show the scan matching algorithm. The scan matching algorithm is used for matching the data between two scans. And the scan matching algorithm helps the slant figure the real-world position and the scan from sensors. In G mapping, the iterative close point is used as the scan matching algorithm. So this figure shows the mating process. The blue line shows the real-world landmark, and the red line shows the scanning data. So the key idea of ICP is that if it knows the correct correspondence, the right relative rotation and the translation can be computed in closed form. If the initial point of QI and the PI were not close enough, the result would be divergent. So adaptive resampling only resample each the threshold of particle number below the threshold of n divided by 2, where n denotes the number of particles. For each particle, the correspondent mapping estimate observation model is computation based on the trajectory of that sample and the history of observations. Next, I will show you the quantum behaved particle swarm optimization idea. First, each particle is depicted by a wave function. In quantum world, the position and the velocity of particle cannot be determined simultaneously. The goal is to improve the search ability and prevent getting into the local minima. So based on the equation 14, we can obtain the position of the particle in next time. And in equation 15, m best denotes the mean best position at the t-test iteration. And equation 16 denotes the position of the particle, where based on the local based position and the global based position combination. So next, I will introduce the open slang algorithms. The open slang algorithms, the purpose is to provide a platform for slang studies, which gives the possibility to publish the algorithms. So here will be the G-mapping algorithms we use, and the slide shows the scan matching score. And we define the fit functions of QPSO. So first, particles' performance will be evaluated, and we use the particles with best fitness to generate the electric mapping. The higher score means the better performance. So figure 8 shows a flow chart of the combination algorithms. We combine the QPSO and the G-mapping algorithms. And the next will be the G-mapping on Rose environment. So here is the result. We use the Gazebo software to execute the simulation. The table 1 lists the parameters of simulation. Here we use the 40 particles, and the minimum score will be 200. And the table 6 lists the parameters of QPSO. The contraction coefficient beta will be random number between the interval of 0 and 1. So figure 11 and figure 12 will be the comparison between two slang results. Figure 11 shows the QPSO G-mapping result, and figure 12 shows the G-mapping particle with particle number equal to 10. So we can see that the result based on QPSO will be better than that of result based on traditional G-mapping. So we can see the similar result on different particle number. So table 7 lists the scan matching score of simulation. We can see that the QPSO G-mapping, the score are always higher than those of traditional G-mapping. And the next will be the experimental result. Here is the testing environment. So we use the quadrotor to do the slang by using QPSO and G-mapping. So table 8 and table 9 list the parameters of implementation. So table 14 lists the scan matrix score. Again, we can see that no matter how the number of particles, the QPSO G mapping are always higher than the result of traditional G mapping. Next will be the conclusion. So the odometry is replaced by the laser scan matrix, and the scan region of QPSO G mapping is larger than the traditional G mapping algorithm. And the tendency of QPSO G mapping is more stable than the tendency of traditional G mapping. And thank you for your attention. Thank you. Is there any question? Okay, if you have any question, please feel free to contact me by email. Thanks.
Oh, sorry. Okay, so let me get started. Uh, it, because my section is a two-page abstract, so I didn't expect to have the presentation in this huge room, the same as the keynote speaker, and with this very large screen. So good afternoon, everyone. My name is Yan Chen Liu. I come from National Cheng Kung University. Today I'm going to share one of my research in the lab, and the title is Adaptive Neural Network-Based Impedance Control of Mobile Manipulators with Uncertainties. So we use robotic system a lot. So the robotic system can be utilized in the manufacturing process, and then to help us to produce different kind of products. But the problem of manipulator is that it's stationary. It cannot move to a different place, so that the workspace is limited. So to solve the problem, we want to focus on the system that's so-called a mobile manipulator, which is a robotic arm mounted on a mobile base. So with the mobile base, we can overcome the limit working area of the fixed base manipulator, so as to increase manipulability and enhance the mobility of the system. And with the mobile manipulator, we can it's possible to extend the applications to not only for the stationary robotic arm, but also can make the robot move around. For example, like in the figure here, we can put the mobile manipulator in the farm, in the acres, to pick up the fruit, okay? Or we can put that in the factory. So the mobile manipulator can move around to pick up the object and then to do different operation. But the problem of mobile manipulator is that it can move around, okay? So different from stationary robotic system, the workspace is large. So if the workspace is large, which means that there will be a lot of different uncertainties. So to deal with that, we want to combine the idea so-called the teleoperation. So we want to use human intelligence for real-time guidance for the mobile manipulator, so that the mobile manipulator moving around under the control of the human. And then this will be leading to the direction of so-called long-distance human-robot interaction. So the study of teleoperation, hold on, it's not, okay. Okay, so the study of the teleoperation on mobile manipulator has been developed for a while, but the main system, the main research direction is for the human to control the mobile base based on the velocity level control. In addition to that, some of the system, they control the mobile base and robotic arm separately. For example, in the image on the right, on the left, you can see that the human holding two local devices. One is controlling the mobile base, another one is controlling the robotic arm. But the problem is that mobile manipulator is a highly dynamic system. So the dynamic model of the arm and, so the dynamic model of the arm and the mobile base should be combined together to develop the controller. So on the right-hand side, the video is the research from our previous work. And then the human can hold the controller to control the mobile platform and the robotic arm. But the problem is that we need to control that individually. So if we want the mobile manipulator to pick up some objects far away, we need to first control it by commanding the mobile base, and then when the robot is close enough, then we switch to the manipulation mode. But the problem is that because the workspace is large, and the human is not co-located with the robot, we don't know whether the robot is close enough to the object, to the workspace we want the robot to handle. So due to that, we want to extend to a different direction. That's so-called the whole body impedance control. Let me focus on whole body. We want to include the dynamic of the mobile base and the robotic arm, and then to become the whole system. So while the human commanding any factor of the arm, then the mobile base will accommodating to the motion, moving around with that. Another one is for impedance control. Because the robot might interact with some objects or even touch the wall in the remote environment. And then if we only control the position, the force from the robot to the wall to the object might be too large. So we need to consider both the position and force. So that leads to the so-called impedance control. And then, the motivation for this research is whole body impedance control of mobile manipulator. And then in the previous research for impedance control, most of the research, they assume that the dynamic model is well known, so all the parameters inside can be obtained. But the problem is that when the robot is moving around, or we use different robot, or even the robot pick up an object, the dynamic system will be different. So in this research, we want to take into consideration the dynamic uncertainty. And then for the human part, because human is far from the robot, so we need to provide enough information for the human to understand what's going on about the robot. So to provide such an intuitive and immersive teleoperation, we combine the mixed reality, which is MR, in Unity 3D, so that the human can understand what's going on. Okay, so this is the main motivation for this research. And the objective, so by concluding what I mentioned, so the objective is whole body control, compliance, dynamic uncertainty, and provide a better operation experience. In addition to that, mobile manipulator, our control is on the any factor. So based on that, the whole system is so-called a redundant system. Redundant system, we can have more the degree of freedom in the null space. Then we can use those null space degree of freedom to accomplish different kind of tasks. So this is called the redundancy. So we will also consider that in this research. And this is the system architecture of our teleoperation mobile manipulator. So the human will put the head-mounted devices, and then in the devices he can see the environment surrounding the mobile manipulator, and the human would also hold two touch handles on the right and on the left. Then during the operation, the operator can decide to switch between the local motion mode and the whole body control mode. For the local motion mode, the human only controls the mobile base. During that operation, the arm is fixed. And then after the mobile manipulator is close enough to the destination or the desired location, then we switch to the whole body control mode. In whole body control mode, the human controls any factor of the mobile base, and the configuration of the robotic arm or even the mobile platform will be autonomously running, okay, under the proposed controller. So in the robot parts, we will feed the position, velocity, and also the image from the any factor to the human-mounted devices, so that the operator can see what's going on. And inside the system, the mobile base is a differential drive mobile robots, and the robotic arm we use here is a Kinova 7 degree of freedom arm. And then the first one, we focus on the human part because the human use head-mounted devices and two touch handled. So we first need to get the precision command from the two hands so that we can use the hand motion to control the mobile robot. So we use the coordinates on the head-mounted devices and then the coordinate on the two touch handle to generate the desired precision and the desired orientation. So this is the transformation, the coordinate transformation we use in Unity 3D because we will get the first position, and by using the quaternion, then we can get the position of the any factor, which will be the position of the touch controller. And then another one is for the orientation. So I'm not going to the detail here, but from this structure, we can get the desired precision and the desired orientation from the human. Then after that, we are going to focus on the mobile manipulator and its dynamics. The left-hand side, the first one, admittance interface is used to model the mobile base. So the mobile platform itself has 3 degrees of freedom, the X, Y position, and the orientation. So then we can use the admittance interface to get this model. And for the mobile base, we don't want the robot to hit the ground or hit a person around, so we can design a so-called visual torque command, tau P, to limit the motion of the mobile base. The second one, The second equation on the left is the dynamic model for the manipulator, so which is the generalized Euler-Lagrange equation. So here we can have the degree of freedom based on the degree of freedom to design the joint space model. So by combining the mobile platform and the manipulator, we can have the synthesized dynamic model for mobile manipulator. So that's the one on the left bottom. So inside the model, we can see that AXT is the external force. This force is applied to the end effector of the robotic arm. So this force will be projected to the two different degree of freedom in the robotic system, so that we need to have the Jacobian matrix. So all the equation on the right is in the joint space. But when we control the robots, we control it on the text space. So we need to convert the dynamic model to the text space. So on the right, in the second equation, this is the text space dynamics. And then for the M matrix, which is inertial matrix, centrifugal force, or the matrix gravitational force G, then we can use the corresponding Jacobian matrix to obtain. Then after we have the text space dynamics, the next one is to propose the whole body impedance control. So for the whole body impedance control, we assume that the human is using the torch to generate the desired command, desired precision, desired orientation. So this is denoted by XD. So based on XD and based on the robot states, we can have the text-based tracking arrow and the position tracking, velocity and position tracking arrow. Then with that, we can propose the whole body impedance control. So that's tau W in the middle, okay? So the orange parts, they are the mass, the inertial, centrifugal force, and gravitational force, but some of the parameters inside is unknown. So we use the radial basis function neural network to compensate for that. And then on the right, you can see the structure. So we use the Gaussian function and with the RBFNN, and then decide the update load to compensate for W hat, okay? And the green part for the tau S, as I mentioned, the mobile manipulator itself is a redundant system. So inside tau S, we can design so-called the subtask control because we are controlling the end effector. So after the robot's tracking its end effector, its configuration is the mobile heads can move around to the different position. So we can use this null space projection methods according to its redundancy to control the joint limits, joint velocity, or the manipulator's configuration. So with the controller, tau W, we substitute into the text-based dynamic model, then we can have the closed-loop dynamics as shown here. So in the closed-loop dynamics, the first term is the inertia of the impedance control. The second term is the damping of the impedance control, and the last term is the stiffness. So now, even though there are dynamic uncertainty, we can all get its closed-loop dynamics. Then based on this one, we conduct the Lyapunov stability to talk about its performance and whether the system is stable. So inside this is the brief of the theorem. But here says that as long as the parameters here are contingent to this condition, if there is no external force, which means that the end effector of the mobile robot do not touch anything, then the text-based position can track the human command perfectly. And then if there is external force on the end effector, then the position tracking arrow is, the system is still stable and the position tracking arrow is uniformly automatically bounded. So here we show some, the first one is a simulation. So the mobile manipulator's end effector is going to track the red dashed line, okay? But there is a wall during the trajectory. So you can see that when the robotic arm touches the wall, due to the design of impedance control, there will be force generated, which is on in the figure on the bottom right. So you can see that during the gray area, which is the duration that the arm touched the wall, so there will be a force. So the force will push in the robot backward so that the robot will not push in too hard to hit the wall. And this is the performance from our design, the design impedance control. And then in addition to the numerical example, we also conduct experiments. So in this experiment, we command the mobile robot to open the door. In the previous research, we control the mobile base and the robotic arm separately. But in this research, we first switch to locomotion mode, controlling the mobile base to close to the door. And then after that, we switch to the whole body control mode. So in whole body control mode, the human only concern on the end effector, and the mobile base and robotic arm will move autonomously. And this is a video. So you can see that this is locomotion mode. And then when the mobile manipulator is close enough, we switch to whole body control mode. So in the two figure on the right, with the gray area, that's in the whole body control mode. So in the whole body control mode, the human only control any factor, but the mobile base will move around following the human command. Then after the door is open, then we can switch back to locomotion mode. So the arm is fixed, then the human only need to focus on controlling the mobile base. Okay, so inside the video, in the video on the right, on the left, you can also see that this is the, okay, so this part, oh, there's no. So this part is the image that the human can see. So human can see the environment, can see the mobile robots, and also can see what's going on. Okay, so let me jump to the conclusion. So before I'm talking about the conclusion, on the right you can see we have the different experiments. The human arm controlling the mobile manipulator to hold a pen and writing on the whiteboard. So if it's not a impedance control, then the robotic arm might break the pen and then break the whiteboard. So in this research, we propose a mobile manipulator whole body impedance control by taking into account the dynamic uncertainty with the use of radio basis function neural network to compensate for that. In addition to that, we also propose the redundancy-based control so that the mobile manipulator can use its null-space degree freedom to conduct different tasks. And then we also complete the experiments on the human-robot interaction. And then in the future, in this research, we assume there's no delay, but when the robot interacting with the human, the communication parts will become a problem. So in the future, we will take into consideration the time delay or some unreliable issue in the communication network. And then in the proposed controller, we only focus on the holonomic constraint. There's no non-holonomic constraint. So we will extend that and then to see any opportunity for the complex remote mission in the future. Okay, so this is my presentation. Thank you very much. So any questions? Okay, so if you have questions, you can send me an email. Okay, thank you for attending my talk. Thank you.